A star, shining with the brilliance of millions of suns, suddenly collapses under its own weight, unleashing an explosion so powerful it can outshine entire galaxies. This isn't science fiction, it's the reality of a supernova, one of the most awe-inspiring and violent events in the universe. But what happens inside the heart of such an explosion? What secrets lie within the chaos of a dying star? Today, we're going to explore the incredible phenomena that occur at the core of a supernova, where unimaginable forces give birth to the building blocks of the cosmos. From the creation of elements that make up everything around us to the formation of mysterious black holes, the story of a supernova is a tale of destruction and creation on a cosmic scale. Stick around as we uncover the science and wonder behind these celestial explosions and discover how they shape the universe as we know it. This is the heart of a supernova. Let's take a closer look. To truly grasp the spectacle of a supernova, we need to rewind the cosmic clock and explore the life cycle of a star. Picture this: swirling clouds of gas and dust drifting through the vast emptiness of space, slowly collapsing under their own gravity. These clouds, often called nebulae, are the cosmic nurseries where stars are born. As gravity pulls the gas closer together, the core heats up, and when the temperature reaches millions of degrees, nuclear fusion ignites. This is the moment a star is born, lighting up the darkness with its fiery glow. For millions or even billions of years, a star burns steadily, fusing hydrogen into helium in its core. This delicate balance between the crushing force of gravity and the outward pressure of fusion keeps the star stable. But like all things in the universe, stars don't last forever. Over time, they exhaust their hydrogen fuel and the balance begins to shift. Smaller stars, like our Sun, will eventually swell into red giants before shedding their outer layers, leaving behind a glowing core called a white dwarf. But for more massive stars, the story takes a far more dramatic turn. When a massive star runs out of fuel, its core can no longer resist the relentless pull of gravity. The star's outer layers collapse inward, creating unimaginable pressure and heat. This triggers a cascade of events as heavier elements like carbon and oxygen fuse into even denser materials like iron. But here's the catch: iron doesn't produce energy through fusion, it absorbs it. Without the outward pressure to counteract gravity, the core collapses in on itself, setting the stage for a supernova. In a matter of seconds, the star's core implodes, and the outer layers are blasted into space in a cataclysmic explosion. This explosive finale isn't just a spectacle, it's a cosmic factory. The intense heat and pressure during a supernova forge elements heavier than iron, scattering them across the universe. These elements become the building blocks for new stars, planets, and even life itself. So, while a supernova marks the end of one star's life, it also sows the seeds for countless others. And as we'll see next, the aftermath of this explosion holds even more mysteries, from the formation of neutron stars to the birth of black holes. The life cycle of a star is a story of creation, destruction, and rebirth, a cycle that shapes the very fabric of the cosmos. At the heart of every supernova lies a battle of cosmic proportions, a struggle between gravity and nuclear fusion that ultimately decides the fate of a star. For millions of years, these two forces are locked in a delicate dance, with gravity pulling inward and fusion pushing outward. But when a massive star exhausts its nuclear fuel, that balance is shattered. The core, no longer able to resist gravity's relentless pull, begins to collapse. This is the moment when the star's fate is sealed, and the stage is set for one of the most powerful explosions in the universe. As the core collapses, something extraordinary happens. The immense pressure and heat cause atoms to break apart, crushing protons and electrons together to form neutrons. This process releases a flood of ghostly particles called neutrinos, which stream outward at nearly the speed of light. These neutrinos carry away an enormous amount of energy, but they also play a crucial role in the explosion itself. As they escape, they interact with the collapsing material, creating a shockwave that rips through the star's outer layers. This shockwave, traveling at millions of miles per hour, is what ultimately tears the star apart in a blinding flash of light, a supernova. The energy released in these moments is almost beyond comprehension. For a brief time, a single supernova can outshine an entire galaxy, radiating as much energy as the sun will produce over its entire lifetime. But this isn't just a spectacle of light and heat. The extreme conditions inside the collapsing core create environments so intense that they defy our everyday understanding of physics. Matter is compressed to densities so high that a single teaspoon would weigh billions of tons. Temperatures soar to trillions of degrees, forging elements heavier than iron elements like gold, platinum, and uranium that are scattered into space. What's truly remarkable is how these cataclysmic events are both destructive and creative. While a supernova marks the violent end of a star's life, it also seeds the cosmos with the raw materials needed for new stars, planets, and even life. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of ancient stars and scattered by supernova. In this way, every supernova is a cosmic rebirth, a reminder that even in destruction there is creation, but the story doesn't end with the explosion. What remains of the star's core depends on its initial mass. For some, the collapse leaves behind a neutron star, a city-sized object so dense that its gravity bends light. For others, the core collapses further, forming a black hole, a region of space where gravity is so strong that not even light can escape. These remnants are the fingerprints of supernova, lasting evidence of the incredible forces at play. The trigger of a supernova is a testament to the power of physics, a reminder of how the universe operates on scales far beyond our everyday experience. It's a story of balance, collapse, and rebirth, a story that continues to shape the cosmos, one explosion at a time. Supernova might seem like a single, uniform phenomenon, but in reality, they come in different flavors, each with its own origin story and cosmic impact. These celestial explosions are broadly categorized into two main types, Type I and Type Roman II. Understanding the differences between them not only sheds light on how stars live and die, but also reveals the intricate processes that shape the universe. Type I supernova are born from the explosive demise of white dwarfs, the remnants of stars like our Sun. But here's the twist, these white dwarfs aren't alone. They're often part of a binary system orbiting a companion star. Over time, the white dwarf's intense gravity pulls material from its partner, growing heavier and denser. This stolen mass pushes the white dwarf toward a critical threshold known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. Once this limit is crossed, the star can no longer support itself. In a matter of seconds, the white dwarf undergoes a runaway nuclear reaction, igniting a thermonuclear explosion that rips it apart. What's fascinating about Type I supernova is their consistency. Because they all originate from white dwarfs reaching the same critical mass, they tend to shine with a predictable brightness, making them invaluable tools for measuring cosmic distances. Type Roman II supernova, on the other hand, are the dramatic final act of massive stars, those at least 8 times heavier than our Sun. These stars burn through their fuel at a furious pace, fusing lighter elements into heavier ones until they reach iron. As we've seen, iron is a cosmic dead end. It doesn't produce energy through fusion. Without the outward pressure to counteract gravity, the star's core collapses, triggering a shockwave that obliterates the star's outer layers in a spectacular explosion. Unlike Type I supernova, Type Roman II explosions leave behind a visible fingerprint, hydrogen. This is because the outer layers of the star, rich in hydrogen, are blasted into space, creating a luminous shell of gas that glows brightly for weeks or even months. The differences between these two types of supernova go beyond their origins. Type I explosions are incredibly bright but short-lived, while Type Roman II events often produce a sustained glow thanks to the radioactive decay of elements like nickel and cobalt. These variations aren't just academic, they help astronomers decode the history and structure of the universe. For example, the absence of hydrogen in Type I supernova provides clues about the nature of the white dwarf's companion star, while the hydrogen-rich remnants of Type Roman II events tell us about the life cycles of massive stars. But perhaps the most intriguing aspect of supernova diversity is what they leave behind. Type I explosions often scatter heavy elements like iron and nickel across the cosmos, enriching the interstellar medium with the building blocks of planets and life. Type Roman II supernova, meanwhile, can leave behind neutron stars or black holes, depending on the mass of the original star. These remnants become cosmic laboratories, offering insights into the extreme conditions that exist nowhere else in the universe. The existence of these two types of supernova reminds us that the cosmos is far from uniform. It's a dynamic, ever-changing place where stars of different sizes and histories meet their ends in spectacular and varied ways. By studying these explosions, we not only learn about the lives and deaths of stars, but also gain a deeper appreciation for the complexity and beauty of the universe. And as we'll see next, the aftermath of these explosions holds even more surprises, from the formation of exotic objects to the creation of the very elements that make life possible. Deep within the heart of a massive star, a silent drama unfolds, one that will ultimately decide its fate. When the core of such a star can no longer sustain the delicate balance between gravity and nuclear fusion, it begins to collapse under its own immense weight. This isn't a slow, graceful descent. It's a rapid, violent implosion that happens in mere seconds. The core, once a bustling furnace of nuclear reactions, is now a ticking time bomb. As the collapse accelerates, the pressure and temperature skyrocket, compressing matter to densities so extreme that they rival those found in an atomic nucleus. This is the pivotal moment of a Type Roman II supernova, the core collapse. At the center of this collapse is a battle between two forces, gravity and electron degeneracy pressure. Electron degeneracy pressure is a quantum mechanical effect that prevents electrons from being squeezed too close together. It's what keeps white dwarfs stable, but in a massive star, even this force has its limits. As the core contracts, electrons are forced into smaller and smaller spaces until they can no longer resist. They merge with protons, forming neutrons and releasing a flood of neutrinos, ghostly particles that barely interact with matter but carry away an enormous amount of energy. This transformation marks the birth of neutron-rich matter, a bizarre state where neutrons are packed together so tightly that a single teaspoon would weigh billions of tons. The collapse doesn't stop there. As the core continues to implode, it reaches a critical point. If the remaining mass is between about 1.4 and 3 times the mass of the Sun, the collapse halts and a neutron star is born. Neutron stars are among the densest objects in the universe, with gravity so strong that it bends light and warps space-time. But if the core's mass exceeds this limit, no known force can stop the collapse. The core crushes itself further, forming a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. What's truly astonishing is how quickly this transformation occurs. From the moment the core begins to collapse to the formation of a neutron star or black hole, the entire process takes less than a second. Yet, in that fleeting moment, the star's core undergoes a metamorphosis that defies imagination. The ordinary matter we're familiar with, protons, electrons, and atoms, is transformed into something extraordinary. A neutron star's ultra-dense core, or the inescapable grip of a black hole. This core collapse isn't just a destructive event, it's also the catalyst for the supernova explosion. As the core implodes, the outer layers of the star rush inward, only to rebound off the newly formed neutron star or black hole. This rebound generates a shockwave that rips through the star's outer layers, ejecting them into space in a dazzling display of light and energy. In this way, the core collapse is both an ending and a beginning, the death of a star and the birth of something entirely new. The physics behind this process is as fascinating as it is complex. It's a testament to the power of gravity, the strange behavior of matter under extreme conditions, and the delicate balance that governs the life and death of stars. By studying these core collapses, we gain not only a deeper understanding of supernova, but also a glimpse into the fundamental forces that shape our universe. And as we'll explore next, the remnants left behind neutron stars and black holes hold even more secrets, offering clues to the nature of space, time, and matter itself. As the core of a massive star collapses, it unleashes an invisible torrent of particles, neutrinos. These ghostly messengers, born in the heart of a supernova, are so elusive that they can pass through entire planets without a trace. Yet, despite their near invisibility, neutrinos play a starring role in the drama of a supernova. In fact, they carry away an astonishing 99% of the explosion's energy, making them one of the most powerful and mysterious forces in the universe. Neutrinos are unlike any other particle we know. They have no electric charge, almost no mass, and interact so weakly with matter that billions of them stream through your body every second without you ever noticing. During a supernova, trillions upon trillions of neutrinos are released in a single burst, flooding the cosmos. But how do these ghostly particles, which barely interact with anything, contribute to the explosion itself? The answer lies in their sheer numbers and the unique way they interact with the collapsing star. As the core collapses, protons and electrons are crushed together, forming neutrons and releasing a flood of neutrinos. These neutrinos don't just escape into space, they interact with the dense, chaotic material surrounding the core. The sheer density of the collapsing star means that even though neutrinos rarely interact with matter, their overwhelming numbers create a significant effect. Some of these neutrinos scatter off the surrounding material, transferring energy and momentum. This interaction helps to power the shockwave that ultimately tears the star apart, driving the supernova explosion. Detecting these neutrinos, however, is no small feat. Because they pass through matter so easily, capturing them requires incredibly sensitive instruments. Neutrino detectors, often buried deep underground to shield them from other particles, rely on massive volumes of material, like water or liquid scintillator, to catch the rare moment when a neutrino interacts. One of the most famous detections of supernova neutrinos came in 1987, when a star in the Large Magellanic Cloud exploded. For a brief moment, detectors around the world picked up a burst of neutrinos, confirming their role in supernova explosions and giving scientists a rare glimpse into the inner workings of these cosmic events. But neutrinos aren't just messengers of destruction, they're also windows into the fundamental laws of physics. Their behavior challenges our understanding of particle physics and the nature of matter itself. For example, neutrinos come in 3 types or flavors, and they can oscillate or change from one flavor to another as they travel through space. This phenomenon, known as neutrino oscillation, has profound implications for our understanding of the universe, hinting at physics beyond the standard model. Studying neutrinos from supernova offers a unique opportunity to explore these mysteries. Because they escape the collapsing star almost immediately, they provide a real-time snapshot of the processes happening deep inside. In contrast, light from the explosion takes longer to emerge, as it must fight its way through the star's outer layers. Neutrinos, therefore, are the first and most direct witnesses to a star's final moments, carrying information about the core's temperature, density, and composition. The story of neutrinos is one of both mystery and discovery. They remind us that even the most elusive particles can have a profound impact, shaping the universe in ways we're only beginning to understand. As we continue to study these ghostly messengers, we uncover not only the secrets of supernova, but also the hidden truths of the cosmos itself. And while neutrinos may be fleeting and hard to detect, their significance is anything but invisible. As the core of a massive star collapses, the shockwave it generates becomes the star's final act of defiance, a force of unimaginable power that rips through the outer layers, scattering them into the void. This shockwave, born from the energy of the core collapse and the torrent of neutrinos, is the true engine of a supernova. It's not just a wave of destruction. It's a sculptor of the cosmos, carving intricate structures and seeding the universe with the building blocks of new stars, planets, and even life. Picture the shockwave as a cosmic tsunami racing outward at millions of miles per hour. It begins at the core, where the collapse creates a sudden, intense burst of energy. This energy is carried outward by neutrinos, which interact with the dense material surrounding the core, transferring their momentum and powering the shockwave. But the journey isn't smooth. As the shockwave moves through the star's layers, it encounters instabilities, turbulent regions where the material is uneven or clumpy. These instabilities can cause the shockwave to stall, but the flood of neutrinos reignites it, pushing it forward with renewed force. One of the most fascinating aspects of this process is how the shockwave shapes the star's material as it travels. The intense pressure and heat create complex structures like jets and filaments, twisting and swirling in patterns that resemble cosmic fireworks. Jets, narrow streams of high-energy particles, can shoot out from the poles of the collapsing star, while filaments, long, wispy strands of gas, stretch across the expanding debris. These structures aren't just beautiful, they're evidence of the immense forces at work, revealing how the shockwave interacts with the star's layers. But the shockwave's impact doesn't stop at the star's surface. When it finally reaches the outer layers, it blasts them into space at incredible speeds, scattering gas and dust across vast distances. This material, enriched with heavy elements forged in the star's core, becomes part of the interstellar medium, the raw material for new stars and planets. In this way, the shockwave is both a destroyer and a creator, tearing apart an old star while laying the groundwork for new ones. What's truly remarkable is how much we've learned about these shockwaves through observations and simulations. By studying the light from supernova, astronomers can trace the shockwave's progress, mapping its speed and intensity. Computer models, meanwhile, allow us to recreate the complex interplay of forces, showing how instabilities and neutrino interactions shape the explosion. These tools have revealed that no two supernovae are exactly alike. Each shockwave leaves its own unique imprint on the star's remains. The shockwave is a testament to the power of physics, a reminder that even in the chaos of a supernova, there are patterns and processes we can understand. It's a force that reshapes not just stars but the fabric of the universe itself, scattering the seeds of creation across the cosmos. And as we'll explore next, the remnants left behind by these explosions, neutron stars and black holes hold even more mysteries, offering clues to the nature of space, time, and the very essence of matter. When a star explodes, it doesn't just light up the sky, it becomes a cosmic factory, forging the very elements that make up the world around us. This process, known as nucleosynthesis, is one of the most extraordinary outcomes of a supernova. Inside the heart of these explosions, temperatures soar to trillions of degrees, and pressures reach levels so extreme that they defy imagination. It's here, in this crucible of chaos, that the building blocks of the universe are born. During a supernova, the intense heat and pressure create the perfect conditions for nuclear reactions to occur. These reactions don't just produce energy, they transform lighter elements into heavier ones, creating everything from the oxygen we breathe to the gold in our jewelry. This process begins with the fusion of hydrogen and helium, but in the fiery aftermath of a supernova, it goes far beyond that. Elements like carbon, oxygen, and nitrogen, which are essential for life, are forged in the outer layers of the star. But the real magic happens deeper inside, where the conditions are even more extreme. One of the key mechanisms at play is something called rapid neutron capture, or the R process. In this process, atomic nuclei are bombarded with neutrons at such a high rate that they can't decay fast enough. As a result, they absorb these neutrons, growing heavier and heavier until they form elements like gold, platinum, and uranium. These heavy elements, which are rare and precious on Earth, are created in a matter of seconds during the explosion. Without supernova, these elements simply wouldn't exist. But nucleosynthesis doesn't stop there. The shockwave from the explosion carries these newly formed elements outward, scattering them across the cosmos. This process, known as stellar enrichment, seeds the interstellar medium with the raw materials needed for new stars, planets, and even life. Over billions of years, these elements are incorporated into new generations of stars and planetary systems, becoming part of the cosmic cycle of creation and destruction. What's truly remarkable is how interconnected everything is. The iron in your blood, the calcium in your bones, and the silicon in the ground beneath your feet all owe their existence to supernova. These explosions are not just in points in the life of a star, they're also starting points for new possibilities. Without them, the periodic table would be far less diverse, and the universe as we know it would look very different. By studying nucleosynthesis, we gain a deeper understanding of not only how elements are formed, but also how they shape the cosmos. It's a reminder that even in the most violent events, there is a profound beauty and purpose. Supernova are more than just explosions, they are the architects of the universe, crafting the very elements that make life possible. And as we'll see next, the remnants left behind by these cosmic forges hold even more secrets, offering clues to the nature of matter, energy, and the universe itself. When a supernova's light fades, the story is far from over. What remains is a cosmic echo, a supernova remnant expanding into the void, carrying the legacy of the explosion across the universe. These remnants, often breathtaking in their beauty, are more than just relics of destruction. They are dynamic, evolving structures that continue to shape the cosmos long after the initial blast. Take, for example, the Crab Nebula, a glowing cloud of gas and dust that was once a star. It's a vivid reminder that even in death, stars leave behind something extraordinary. The life of a supernova remnant begins with what's known as the free expansion phase. In this early stage, the shockwave from the explosion races outward at incredible speeds, sweeping up the surrounding interstellar material like a cosmic snowplow. The remnants expand freely, unhindered by external forces, creating a shell of hot, ionized gas that glows brightly in X-rays and radio waves. This phase can last for hundreds or even thousands of years, depending on the size of the explosion and the density of the surrounding medium. As the remnant expands, it eventually encounters resistance from the interstellar medium, the thin gas and dust that fill the space between stars. This marks the transition to the adiabatic or Sedov-Taylor phase. Here, the shockwave slows down and the energy from the explosion is converted into heat and motion. The remnant begins to cool and its structure becomes more complex, with intricate filaments and bubbles forming as the shockwave interacts with the surrounding material. It's during this phase that some of the most iconic images of supernova remnants are captured, showcasing their intricate beauty. But the evolution doesn't stop there. Over time, the remnant enters the radiative phase where cooling becomes the dominant process. The gas, now much cooler, begins to emit visible light, creating the glowing, colorful structures we often associate with supernova remnants. This phase can last for tens of thousands of years, during which the remnant continues to expand and interact with its environment. It's a slow, graceful process, a stark contrast to the violent explosion that started it all. One of the most fascinating aspects of supernova remnants is their role as cosmic laboratories. They are rich in heavy elements like iron, silicon, and oxygen, forged in the heart of the explosion and scattered into space. These elements become part of the interstellar medium, enriching it with the raw materials needed for new stars and planets. But remnants also offer a unique opportunity to study the physics of shockwaves, particle acceleration, and even the origins of cosmic rays. By observing how remnants evolve and interact with their surroundings, scientists can piece together the story of the explosion and its aftermath. Supernova remnants are more than just relics of the past. They are active participants in the life cycle of the universe. They shape the interstellar medium, trigger the formation of new stars, and continue to influence the cosmos long after their parent star has vanished. From the glowing filaments of the Crab Nebula to the vast, expanding shells of older remnants, these structures are a testament to the enduring power of stellar explosions. They remind us that even in the wake of destruction, there is creation, beauty, and a story that continues to unfold. When the dust settles after a supernova, what remains is often as extraordinary as the explosion itself. The dying star doesn't just vanish, it leaves behind a cosmic legacy, a remnant that defies imagination. For some stars, this legacy takes the form of a neutron star, an object so dense that it pushes the limits of physics. For others, the aftermath is even more mysterious, a black hole, a region of space where gravity reigns supreme, and the laws of the universe as we know them break down. These remnants aren't just relics of destruction, they are windows into the extreme, offering clues about the nature of matter, gravity, and the cosmos itself. Neutron stars are among the most bizarre objects in the universe. Picture a star several times more massive than our Sun, crushed into a sphere no larger than a city. The sheer density of a neutron star is mind-boggling. Just a teaspoon of its material would weigh billions of tons. This incredible density is the result of the star's core collapsing under its own gravity, forcing protons and electrons to merge into neutrons. What's left is a neutron-rich core, a cosmic pressure cooker where matter is packed so tightly that it behaves in ways we're only beginning to understand. But neutron stars aren't just dense, they are also incredibly dynamic. Many neutron stars spin at dizzying speeds, completing hundreds of rotations every second. Some emit beams of radiation from their magnetic poles, creating pulsars that flash like cosmic lighthouses as they spin. These pulsars are so precise in their timing that they rival atomic clocks, making them invaluable tools for studying the universe. And then there are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These cosmic powerhouses can unleash bursts of energy so intense that they can be detected halfway across the galaxy. On the other end of the spectrum are black holes, the ultimate cosmic enigmas. When a star's core collapses beyond the point where even neutrons can hold it together, no known force can stop the implosion. The core crushes itself into a singularity, a point of infinite density where the laws of physics as we know them cease to apply. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. Once something crosses this threshold, it's gone forever, swallowed by the black hole's insatiable gravity. Despite their ominous reputation, black holes play a crucial role in shaping the universe. They are cosmic engines capable of powering some of the most energetic phenomena we've observed. When matter falls into a black hole, it doesn't just vanish, it forms an accretion disk, a swirling maelstrom of superheated gas that emits intense radiation. In some cases, this process can produce jets of particles that shoot out at nearly the speed of light, carving through space and influencing the formation of galaxies. Black holes are also thought to lie at the heart of most galaxies, including our own Milky Way, where they act as gravitational anchors, shaping the motion of stars and gas on a cosmic scale. What makes these remnants so fascinating is how they challenge our understanding of the universe. Neutron stars and black holes exist in realms where gravity and quantum mechanics collide, creating conditions that we can't replicate on Earth. By studying them, we gain insights into the fundamental forces that govern the cosmos. They are not just the ashes of dead stars, they are cosmic laboratories, offering a glimpse into the extremes of nature. The story of a supernova doesn't end with the explosion. It's a tale of transformation where the death of a star gives birth to something entirely new. Whether it's a spinning neutron star or a voracious black hole, these remnants remind us that even in destruction there is creation. They are the fingerprints of the universe's most violent events, and their mysteries continue to inspire and challenge us, driving our quest to understand the cosmos. As we'll see next, the echoes of these explosions ripple far beyond their immediate aftermath, shaping the universe in ways we're only beginning to comprehend. Supernova are more than just spectacular cosmic fireworks. They are the architects of the universe, shaping its evolution on a grand scale. Every time a star explodes, it sends shockwaves through the cosmos, scattering heavy elements like iron, gold, and uranium into the surrounding space. These elements, forged in the heart of the explosion, become the building blocks for new stars, planets, and even life itself. Without supernova, the universe would be a very different place, darker, emptier, and far less diverse. One of the most profound ways supernova influence cosmic evolution is by enriching the interstellar medium, the vast, diffuse clouds of gas and dust that fill the space between stars. When a supernova explodes, it blasts its outer layers into space, carrying with it a mix of elements that were once locked deep inside the star. These elements, now free to mingle with the surrounding gas, become part of the raw material for future generations of stars and planets. Over billions of years, this process has transformed the universe from a sea of hydrogen and helium into a rich tapestry of elements, giving rise to the complex structures we see today. But the impact of supernova doesn't stop there. The shockwaves from these explosions also play a key role in triggering the formation of new stars. As the shockwave travels through the interstellar medium, it compresses the gas and dust, creating dense regions where gravity can take hold. These regions, known as molecular clouds, are the birthplaces of stars. In this way, supernova not only provide the ingredients for new stars, but also the spark that ignites their formation. It's a cosmic cycle of destruction and creation, where the death of one star gives rise to countless others. On an even larger scale, supernova influence the structure and evolution of entire galaxies. The energy released by these explosions can heat the interstellar gas, preventing it from collapsing into new stars and regulating the rate of star formation. In some cases, supernova can even drive galactic winds, pushing gas out of a galaxy entirely and shaping its overall structure. This process, known as feedback, helps explain why some galaxies are teeming with young, bright stars while others are quieter and more quiescent. Perhaps the most remarkable aspect of supernova is how they connect the past, present, and future of the universe. The elements they scatter become part of new stars and planets, some of which may one day host life. The shockwaves they produce trigger the birth of new stars, continuing the cycle of stellar evolution, and the energy they release shapes the galaxies they inhabit, influencing the course of cosmic history. In this way, supernovae are not just endpoints in the life of a star, they are also starting points for new possibilities. The story of supernova is a story of transformation. It's a reminder that even in the most violent events, there is a profound beauty and purpose. These explosions are the driving force behind the evolution of the cosmos, shaping the universe in ways we're only beginning to understand. From the birth of stars to the formation of galaxies, supernovae are the unseen hand that guides the universe's journey through time and space. And as we continue to explore their mysteries, we uncover not only the secrets of the cosmos but also our own place within it. Detecting a supernova is no small feat, especially when you consider that these cosmic explosions can happen anywhere in the vast expanse of the universe. Yet, astronomers have developed an impressive array of tools and techniques to spot these fleeting events, often catching them in the act. The hunt begins with telescopes both on the ground and in space, scanning the skies for sudden bursts of light. When a supernova occurs, it can outshine entire galaxies, making it visible even from billions of light years away. But spotting the explosion is just the first step. To truly understand what's happening, scientists need to capture and analyze every detail of the event. One of the most critical tools in this effort is the light curve, a graph that tracks how a supernova's brightness changes over time. By measuring the intensity of light at different wavelengths, astronomers can piece together the story of the explosion. For example, Type Ia supernova, which result from the detonation of white dwarfs, have a distinctive light curve that rises sharply, peaks, and then gradually fades. This predictable pattern makes them invaluable as standard candles for measuring cosmic distances. On the other hand, Type Roman II supernova, which originate from massive stars, often show a slower decline in brightness, reflecting the complex processes happening within the star's core. By studying these light curves, scientists can determine not only the type of supernova, but also its distance, energy output, and even the elements produced in the explosion. But light curves are just one piece of the puzzle. To get a fuller picture, astronomers also use spectroscopy, a technique that breaks down the light from a supernova into its component colors. Each element leaves a unique fingerprint in the spectrum, allowing scientists to identify which elements are present and in what quantities. This information reveals the inner workings of the explosion, from the nuclear reactions that forged heavy elements to the shockwaves that propelled them into space. Spectroscopy also provides clues about the star's environment, such as the presence of gas clouds or the remnants of previous stellar explosions. Of course, not all observations are made from Earth. Space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory offer a clear view of supernova without the interference of Earth's atmosphere. These instruments can detect wavelengths of light like ultraviolet and X-rays that are invisible from the ground, providing insights into the high-energy processes at play. For instance, X-ray observations have revealed the presence of shockwaves heating the surrounding gas, while ultraviolet light has exposed the rapid expansion of the supernova's outer layers. The study of supernova isn't just about understanding individual explosions, it's about piecing together the larger story of the universe. By observing these events, astronomers can test theories of stellar evolution, refine models of how stars live and die, and even probe the nature of dark energy, the mysterious force driving the universe's accelerated expansion. Each supernova is a cosmic experiment, offering a glimpse into the fundamental forces that shape our reality. What's truly remarkable is how far we've come in our ability to observe and analyze these events. From humble beginnings with the naked eye to today's cutting-edge telescopes and detectors, the tools of astronomy have transformed our understanding of the cosmos. And as technology continues to advance, the secrets of supernova are becoming clearer. revealing not only the mechanics of these explosions, but also their profound impact on the universe as a whole. The study of supernova is more than just a scientific pursuit. It's a journey into the heart of the cosmos, where every explosion tells a story, and every observation brings us closer to understanding our place in the vast tapestry of space and time. Long before telescopes or modern science, humans gazed up at the night sky and witnessed moments of celestial brilliance that defied explanation. Among these were supernova explosions so bright they could outshine entire constellations, leaving an indelible mark on the cultures that observed them. One of the most famous of these events occurred in the year 1054, when a star in the constellation Taurus erupted into a spectacle so dazzling it could be seen even in broad daylight. This was the Crab supernova, an explosion that transformed the way people thought about the heavens and left behind a glowing remnant we now call the Crab Nebula. The Crab supernova wasn't just a scientific curiosity, it was a cultural phenomenon. Chinese and Japanese astronomers meticulously recorded the event, describing it as a guest star that appeared suddenly and lingered for weeks before fading. Indigenous peoples in the Americas may have also observed the explosion, weaving it into their myths and stories. These records are invaluable to astronomers today, offering a glimpse into the life cycle of stars and the processes that drive supernova. The Crab Nebula, the glowing remains of that explosion, continues to captivate scientists and stargazers alike, serving as a living testament to the power of these cosmic events. Fast forward to the year 1604, and another supernova lit up the night sky, this time in the constellation Ophiuchus, known as Kepler's supernova, after the renowned astronomer Johannes Kepler, who studied it extensively. This explosion was visible for over a year and became a turning point in the history of astronomy. At the time, the prevailing belief was that the heavens were unchanging, a perfect and eternal realm. But Kepler's supernova shattered that notion, proving that the cosmos was dynamic and ever-evolving. Kepler's observations, combined with those of other astronomers, laid the groundwork for our modern understanding of stellar explosions and their role in the universe. These historical supernovae weren't just scientific milestones. They were moments of wonder that connected people across cultures and generations. They inspired art, literature, and even religious interpretations as societies sought to make sense of these celestial spectacles. In many ways, they were humanity's first steps toward understanding the cosmos, sparking a curiosity that continues to drive our exploration of the universe today. What's truly remarkable is how these ancient observations align with modern science. The Crab Nebula, for instance, is now known to harbor a pulsar, a rapidly spinning neutron star, at its heart, while Kepler's supernova left behind a remnant rich in heavy elements like iron and silicon. By studying these remnants, astronomers can piece together the story of the explosions that created them, bridging the gap between past and present. These historical supernovae remind us that the universe is not just a place of distant stars and galaxies, it's a living, evolving entity that we are only beginning to understand. The legacy of these celestial events extends far beyond their immediate impact. They shaped our ancestors' understanding of the cosmos, challenged long-held beliefs, and paved the way for the scientific discoveries that define our modern era. And as we continue to explore the universe, we carry forward the same sense of wonder and curiosity that inspired those who first witnessed these cosmic explosions. The story of supernova is not just a tale of stars, it's a story of humanity's enduring quest to understand the mysteries of the universe. The night sky has always been humanity's first storybook, filled with tales of gods, heroes, and cosmic events that shaped our ancestors' understanding of the universe. Among these celestial narratives, supernova held a special place, explosions so bright and sudden that they seemed to carry messages from the heavens. Across cultures and continents, these dazzling events were often interpreted as omens, divine signs, or even the actions of powerful beings. From the meticulous records of Chinese astronomers to the rich oral traditions of Native American tribes, supernova became more than just astronomical phenomena. They became myths, legends, and symbols of the profound connection between humanity and the stars. In ancient China, where astronomy was deeply intertwined with astrology and governance, supernova were seen as harbingers of change. The Chinese referred to these events as guest stars, celestial visitors that appeared suddenly and then faded away, often leaving behind a sense of awe and mystery. The supernova of 1054, which created the Crab Nebula, was meticulously documented by Chinese astronomers who described it as a star as bright as Jupiter that lingered for nearly 2 years. To them, this cosmic event was not just a scientific curiosity, it was a sign, a message from the heavens that could foretell the rise or fall of emperors, the stability of kingdoms, or the fate of entire dynasties. The Chinese believed the heavens reflected the order or disorder of the earthly realm, and supernova were seen as powerful disruptions in that cosmic balance. Halfway across the world, Native American tribes also observed and interpreted supernova through the lens of their own rich mythologies. For the Zuni people of the American Southwest, a supernova might have been seen as the fiery breath of a celestial being, while the Navajo wove such events into their stories of the hero twins who journeyed through the heavens to bring light and order to the world. These cultures saw the stars not as distant, impersonal objects, but as living entities, part of a vast, interconnected web of life. A supernova, then, was not just an explosion, it was a moment of cosmic transformation, a reminder of the ever-changing nature of the universe and humanity's place within it. In Europe, the supernova of 1604, now known as Kepler's supernova, was also steeped in cultural significance. At a time when the heavens were believed to be unchanging and perfect, the sudden appearance of a new star challenged long-held beliefs and sparked intense debate. Astronomers like Johannes Kepler saw it as an opportunity to study the cosmos, but for many others it was a sign of divine intervention, a warning, a blessing, or perhaps a call to reflect on the mysteries of existence. This explosion, visible for over a year, became a symbol of the tension between tradition and discovery, between faith and science, as humanity grappled with the implications of a dynamic, ever-evolving universe. What's fascinating about these cultural interpretations is how they reveal a universal human impulse to find meaning in the stars. Supernova, with their sudden brilliance and fleeting nature, captured the imagination of people across time and geography, inspiring stories that connected the celestial and the terrestrial. These myths and legends remind us that science and storytelling are not so different. Both seek to explain the world around us, to make sense of the unknown, and to explore our place in the cosmos. The intersection of science and mythology offers a unique lens through which to view supernova. While modern astronomy provides us with a detailed understanding of the physics behind these explosions, the myths and stories of the past remind us of their emotional and cultural impact. They tell us that supernova are more than just cosmic events. They are moments of wonder that have shaped human thought, art, and spirituality for millennia. By exploring the cultural legacy of supernova, we not only deepen our appreciation for these celestial phenomena, but also gain insight into the enduring human connection to the stars, a connection that continues to inspire and guide us as we reach for the heavens. When we think of life on Earth, we often picture the lush forests, vast oceans, and diverse ecosystems that make our planet so unique. But the story of life begins long before the first cell formed. It starts in the hearts of dying stars. Supernova, those titanic explosions that mark the end of a star's life, are also the cosmic forges where the very elements necessary for life are created. From the carbon in our DNA to the oxygen we breathe, the building blocks of life owe their existence to these cataclysmic events. So, could supernova have played a role in the origin of life on Earth? The answer lies in the chemistry of the cosmos. At their core, supernova are factories of creation. The intense heat and pressure generated during these explosions allow atoms to fuse into heavier elements, transforming simple hydrogen and helium into the complex tapestry of the periodic table. Elements like carbon, nitrogen, and oxygen, essential for life as we know it, are forged in the fiery hearts of massive stars and scattered across the universe when those stars explode. Over billions of years, these elements become part of the interstellar medium, the raw material for new stars, planets, and ultimately life. Without supernova, the universe would be a far simpler place, devoid of the chemical diversity that makes life possible. But how did these elements make their way to Earth? The journey begins with the formation of our solar system. When a massive star explodes, it seeds its surroundings with the heavy elements it created. These elements mix with clouds of gas and dust, which eventually collapse under gravity to form new stars and planets. Our Sun and its planets, including Earth, are the products of this process. The iron in Earth's core, the silicon in its crust, and the oxygen in its atmosphere all trace their origins back to ancient supernova. In a very real sense, we are made of stardust, a legacy of the stars that came before us. The connection between supernova and life doesn't end with the formation of Earth. These explosions also influence the conditions necessary for life to thrive. For example, the radioactive elements produced in supernova, such as uranium and thorium, generate heat as they decay. This heat helps drive the geological activity that shapes our planet, from the movement of tectonic plates to the creation of mountains and oceans. Without this internal heat, Earth might have remained a cold, lifeless rock. Supernova, in their own way, helped create the dynamic, ever-changing world that makes life possible. What's even more fascinating is the possibility that supernova might not just be a prerequisite for life on Earth. They could also play a role in the existence of life elsewhere in the universe. If the heavy elements forged in these explosions are essential for life, then planets orbiting stars born from the remnants of supernova are more likely to have the right ingredients for biology. This raises an intriguing question. Could supernova be a universal catalyst for life? While we don't yet have the answer, the idea that these explosions might be a common thread in the story of life across the cosmos is both inspiring and humbling. Supernova remind us that the universe is a place of both destruction and creation. While they mark the violent end of a star's life, they also sow the seeds for new beginnings. From the elements they create to the planets they shape, these explosions are woven into the very fabric of existence. They are a testament to the interconnectedness of all things, a reminder that life on Earth, and perhaps elsewhere, is part of a much larger cosmic story. As we continue to explore the universe, we may find that supernova are not just the architects of our world, but also the silent partners in the ongoing adventure of life. In the late 20th century, a discovery shook the foundations of cosmology, one that came not from peering into the heart of distant galaxies, but from the light of dying stars. It was the observation of distant supernova, particularly Type Ia events, that unveiled a startling truth. The universe isn't just expanding, it's accelerating. This revelation led to the identification of a mysterious force called dark energy, a discovery that has reshaped our understanding of the cosmos. Type Ia supernova are unique in their consistency. These explosions occur when a white dwarf in a binary system siphons material from its companion star until it reaches a critical mass, triggering a runaway nuclear reaction. Because this process is so predictable, Type Ia supernovas shine with a nearly uniform brightness, making them invaluable tools for measuring cosmic distances. Astronomers refer to them as standard candles, cosmic lighthouses whose light can be used to map the vast expanse of the universe. But it wasn't just their brightness that made these supernovas so revolutionary, it was what they revealed about the universe's expansion. In the 1990s, two independent teams of astronomers set out to measure the distances to distant Type Ia supernova, expecting to confirm that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The supernova were fainter than expected, suggesting they were farther away than predicted. The only explanation, the expansion of the universe was speeding up, driven by an unknown force, dark energy. This discovery was a game-changer. For decades, scientists had assumed that gravity, the force pulling everything together, would eventually slow the universe's expansion. Dark energy, however, behaves in the opposite way, acting as a kind of cosmic repulsion that pushes galaxies apart. It's now believed to make up about 68% of the universe's total energy, dwarfing the contributions of matter and dark matter. Yet, despite its dominance, dark energy remains one of the greatest mysteries in modern science. We know it's there, but what exactly is it? Is it a property of space itself, or something entirely different? These questions remain unanswered, but the study of supernova continues to provide clues. The implications of dark energy are profound. If the universe's expansion continues to accelerate, it could lead to a future where galaxies are so far apart that their light can no longer reach us, leaving the night sky dark and empty. On the other hand, some theories suggest that dark energy could evolve over time, potentially altering the fate of the cosmos in unexpected ways. The study of supernova doesn't just help us understand the past, it gives us a glimpse into the universe's ultimate destiny. What's remarkable is how this discovery underscores the interconnectedness of the cosmos. A dying star billions of light years away can reveal the presence of a force that shapes the entire universe. It's a reminder that even the smallest details, like the brightness of a supernova, can hold the key to understanding the biggest questions. And as we continue to observe and analyze these cosmic explosions, we inch closer to unraveling the mysteries of dark energy and the universe it governs. This is the power of supernova. They are not just the end of stars, but also the beginning of new scientific frontiers, illuminating the darkest corners of our understanding. Supernova aren't just the domain of scientists and astronomers, they've also ignited the imaginations of storytellers, artists, and creators across the globe. These cosmic explosions, with their raw power and beauty, have become powerful symbols in popular culture, often representing both destruction and renewal. Whether in the pages of a novel, the frames of a film, or the brushstrokes of a painting, supernova capture our fascination with the universe's extremes, blending science and art in ways that resonate deeply with audiences. In science fiction, supernova are often depicted as cataclysmic events that reshape entire worlds, or even galaxies. Take, for example, Arthur C. Clarke's classic novel The Songs of Distant Earth, where a supernova's impending destruction forces humanity to flee Earth in search of a new home. Here, the supernova isn't just a plot device, it's a metaphor for the fragility of existence and the resilience of life. Stories like these remind us that even in the face of cosmic destruction, there's always the possibility of rebirth and new beginnings. Filmmakers, too, have been captivated by the drama of supernova. In movies like Interstellar and Star Trek: Generations, these explosions serve as backdrops for epic journeys, pushing characters to confront their limits and rethink their place in the universe. The visual spectacle of a supernova, with its blinding light and swirling debris, lends itself perfectly to the big screen, offering a visceral reminder of the universe's power. But beyond the special effects, these portrayals often carry deeper themes about sacrifice, transformation, and the enduring human spirit. Artists, meanwhile, have used supernova as a source of inspiration, translating their explosive energy into vivid, imaginative works. From abstract paintings that evoke the chaos of a collapsing star to sculptures that capture the moment of explosion, these creations invite us to see supernova not just as scientific phenomena, but as symbols of creativity itself. The process of a star's death and rebirth mirrors the act of creation, breaking down the old to make way for the new. Even in music, supernova have found a place. Bands like Muse and Imagine Dragons have used the imagery of exploding stars to explore themes of passion, intensity, and transformation. In their lyrics, a supernova becomes a metaphor for moments of profound change, whether in love, life, or the human experience. These artistic interpretations remind us that supernova are more than just astronomical events. They're a source of inspiration, a way to connect the vastness of the cosmos to the intimate details of our lives. What makes supernova so compelling in popular culture is their duality. They are both destructive and creative, endings and beginnings. They remind us that even in the face of immense loss, there is potential for something new and extraordinary. This duality resonates with audiences because it mirrors our own experiences of change, growth, and resilience. Whether we're watching a star explode on screen or reading about its aftermath in a novel, we're drawn to the idea that destruction can lead to transformation. The allure of supernova in popular culture isn't just about their visual spectacle or scientific intrigue, it's about what they represent. They are reminders of the universe's grandeur and mystery, symbols of the cycles of creation and destruction that shape not only the cosmos but also our own lives. By exploring these artistic interpretations, we gain a deeper appreciation for how supernova inspire us to dream, create, and imagine. They are not just stars that explode, they are sparks that ignite our collective imagination, lighting up our stories and our understanding of the universe. What does the future hold for supernova research? As technology advances at an unprecedented pace, we're standing on the brink of a new era in our understanding of these cosmic explosions. From cutting-edge telescopes to groundbreaking missions, the tools at our disposal are becoming more powerful, more precise, and more capable of unlocking the secrets of supernova than ever before. The next frontier of discovery is already taking shape, promising to reveal not only how these explosions work, but also how they shape the universe around us. One of the most exciting developments on the horizon is the next generation of space telescopes. Instruments like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are set to revolutionize our ability to observe supernova in unprecedented detail. These telescopes will peer deeper into the cosmos, capturing the faint light of ancient supernova that occurred billions of years ago. By studying these distant explosions, scientists hope to uncover clues about the early universe, how it evolved, how stars formed, and how the first galaxies came together. It's like having a time machine that allows us to witness the universe's most dramatic moments as they unfolded. But it's not just about looking back in time. Future missions are also focused on detecting supernova as they happen in real time. Projects like the Vera-C Rubin Observatory, with its massive camera capable of scanning the entire sky every few nights, are designed to catch these explosions in their earliest stages. By capturing the initial moments of a supernova, scientists can study the shockwaves, the formation of heavy elements, and the behavior of neutrinos in ways that were previously impossible. Imagine being able to watch a star explode almost as it happens, a front-row seat to one of the universe's most spectacular events. Groundbreaking advancements in neutrino detection are also opening new doors. Neutrinos, those elusive particles that stream out of a collapsing star, are key to understanding the inner workings of supernova. New detectors like the Deep Underground Neutrino Experiment (DUNE) are being built to capture these particles with unprecedented sensitivity. By studying the neutrinos from a supernova, researchers can gain insights into the core collapse process, the formation of neutron stars and black holes, and even the fundamental properties of these mysterious particles themselves. It's a window into the most extreme environments in the universe, offering clues that could reshape our understanding of physics. The future of supernova research isn't just about observation, it's also about collaboration. Scientists around the world are working together to create networks of telescopes and detectors, ensuring that no supernova goes unnoticed. These global efforts, combined with advances in artificial intelligence and data analysis, are making it possible to process and interpret vast amounts of information faster than ever before. The result, a deeper, more comprehensive understanding of these cosmic explosions and their role in the universe. What makes this moment so exciting is the sheer potential for discovery. Every new tool, every new mission brings us closer to answering some of the biggest questions in astronomy. How do supernovas shape the evolution of galaxies? What role do they play in the creation of life, and what can they tell us about the fundamental forces that govern the cosmos? The answers are out there, waiting to be found, and the next generation of researchers is ready to uncover them. As we look to the future, one thing is clear: the study of supernova is far from over. It's a field that continues to evolve, driven by curiosity, innovation, and the relentless pursuit of knowledge. With each new discovery, we're not just learning more about these explosive events, we're gaining a deeper understanding of the universe itself, and that perhaps is the most thrilling part of all. The universe is full of mysteries, but perhaps none are as elusive as gravitational waves, ripples in the fabric of spacetime itself. Predicted by Einstein over a century ago, these waves were first detected in 2015, marking a monumental leap in our ability to observe the cosmos. Unlike light, which can be absorbed or scattered, gravitational waves travel unimpeded, offering a completely new way to study the universe. And when it comes to supernova, these ripples in spacetime could revolutionize our understanding of how stars die. Gravitational waves are generated by some of the most violent events in the universe, colliding black holes, merging neutron stars, and potentially the core collapse of massive stars. When a massive star reaches the end of its life and collapses into a supernova, the immense forces at play can create ripples in spacetime. Detecting these waves would allow us to peer directly into the heart of the explosion, revealing details that light alone cannot show. It's like listening to the universe's heartbeat, giving us a real-time view of events that shape the cosmos. But detecting gravitational waves from supernova is no easy task. While mergers of black holes and neutron stars produce strong, distinct signals, the waves from a supernova are far more complex and subtle. The collapse of a star's core is a messy, chaotic process, and the resulting gravitational waves are more like a cacophony than a clear tone. To make matters more challenging, these signals are incredibly faint by the time they reach Earth, requiring detectors of extraordinary sensitivity. Projects like LIGO and Virgo, which made the first gravitational wave detections, are constantly being upgraded to meet this challenge, pushing the boundaries of what's possible. What makes this effort so exciting is the potential to answer questions that have puzzled scientists for decades. For instance, how exactly does a star's core collapse? What role do neutrinos play in the explosion? And how do the shockwaves that tear the star apart form and propagate? Gravitational waves could provide the missing pieces of the puzzle, offering insights that complement what we learn from light and neutrinos. By combining these different observations, we can build a more complete picture of supernova, one that spans the entire spectrum of cosmic signals. The first detection of gravitational waves from a neutron star merger in 2017 gave us a taste of what's possible. This event, dubbed GW170817, not only produced ripples in space-time but also a burst of light across multiple wavelengths from gamma rays to radio waves. It was a groundbreaking moment showing how gravitational waves and traditional astronomy can work together to reveal the universe's secrets. While supernova present a greater challenge, the potential rewards are immense. A successful detection would not only deepen our understanding of these explosions, but also test our theories of gravity and the behavior of matter under extreme conditions. The quest to detect gravitational waves from supernova is a testament to human ingenuity and curiosity. It's a reminder that the universe speaks to us in many ways through light, through particles, and through the very fabric of space-time. By listening to these cosmic whispers, we're not just learning about supernova, we're uncovering the fundamental laws that govern the universe. And as our detectors grow more sensitive and our techniques more refined, the day may come when we can hear the final moments of a dying star, transforming our understanding of these cosmic fireworks forever. When we think about the search for extraterrestrial life, our minds often drift to distant planets, icy moons, or even the possibility of microbial life in our own solar system. But what if the key to finding life beyond Earth lies not just in the planets themselves, but in the stars that surround them? Supernova, those titanic explosions that mark the end of a star's life, might hold surprising clues about the potential for life elsewhere in the universe. From seeding the cosmos with the building blocks of biology to posing existential threats, these cosmic events play a dual role in shaping the habitability of worlds far beyond our own. On one hand, supernova are cosmic alchemists, transforming simple elements into the complex chemistry needed for life. When a massive star explodes, it scatters heavy elements like carbon, nitrogen, and oxygen into the surrounding space. These elements, forged in the heart of the explosion, become part of the interstellar medium, the raw material for new stars, planets, and potentially life itself. Without supernova, the universe would lack the chemical diversity required for biology. In this sense, these explosions are not just destructive, they're also creators, laying the groundwork for the possibility of life on countless worlds. But while supernova provide the essential ingredients for life, they can also pose significant risks. The intense radiation from a nearby supernova could strip away a planet's atmosphere, leaving it barren and lifeless. Gamma-ray bursts, the most energetic explosions in the universe, are thought to be triggered by certain types of supernova and could sterilize entire planetary systems. For a planet to sustain life, it must strike a delicate balance close enough to supernova to benefit from the elements they create, but far enough to avoid their destructive power. It's a cosmic tightrope walk, and the outcome could determine whether a world becomes a cradle of life or a cosmic wasteland. What's fascinating is how this balance might vary across the universe. In regions with frequent supernova, like the dense cores of galaxies, planets might be more likely to receive the heavy elements needed for life, but also face greater risks from radiation. In quieter regions like the outskirts of galaxies, the chances of a nearby supernova might be lower, but so too might the availability of essential elements. This interplay between creation and destruction adds a layer of complexity to the search for extraterrestrial life, forcing us to consider not just where life could exist, but how it might survive in a universe shaped by these explosive events. One intriguing possibility is that supernova could act as catalysts for life in unexpected ways. The shockwaves from these explosions might compress gas and dust, triggering the formation of new stars and planetary systems. In this way, a single supernova could set off a chain reaction of star birth, creating new opportunities for life to emerge. It's a reminder that the universe is a dynamic, interconnected system, where even the most violent events can have far-reaching positive consequences. As we continue to explore the cosmos, supernova will remain a central focus in the search for life beyond Earth. They remind us that the story of life is not just about planets or stars. It's about the intricate dance of creation and destruction that shapes the universe. From the elements they forge to the risks they pose, these cosmic explosions are woven into the very fabric of existence, influencing the potential for life in ways we're only beginning to understand. And as we look to the stars, we're not just searching for other worlds, we're uncovering the profound connections that bind us to the cosmos. What if the universe we see is just one of many? This tantalizing idea, known as the multiverse, has captured the imagination of scientists and dreamers alike. While it might sound like science fiction, some theories suggest that supernova could hold clues about the existence of parallel universes. These cosmic explosions, already shrouded in mystery, might be more than just spectacular events in our own universe. They could be windows into something even grander. At the heart of this idea lies quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales. Quantum mechanics tells us that particles can exist in multiple states at once, a phenomenon known as superposition. But what if this principle extends to the universe itself? Some physicists propose that every possible outcome of a quantum event spawns a new universe, creating an infinite web of parallel realities. This is the essence of the multiverse theory, a vast, branching network of universes, each with its own unique history and laws of physics. So, where do supernova come into play? These explosions are among the most extreme events in the universe, governed by the same quantum laws that underpin the multiverse. When a star collapses, the chaotic interplay of particles and forces could create ripples not just in our universe but across the multiverse itself. Some theories suggest that the energy released during a supernova might leave faint imprints in the fabric of space-time, traces that could hint at the existence of other universes. While this remains speculative, the idea is rooted in the strange and counterintuitive nature of quantum mechanics, which often defies our everyday experience. Another intriguing possibility is that supernova could act as cosmic messengers, carrying information about the multiverse through their light and neutrinos. Neutrinos, those elusive particles that stream out of a collapsing star, are particularly intriguing. Because they interact so weakly with matter, they could potentially travel between universes, offering a glimpse into realities beyond our own. Detecting such signals would require technologies far beyond what we currently possess, but the very notion opens up a realm of possibilities that stretches the boundaries of our imagination. Cosmology, the study of the universe as a whole, also plays a role in this speculative connection. Observations of supernova have already reshaped our understanding of the cosmos, revealing the accelerating expansion of the universe and the mysterious force known as dark energy. Could dark energy itself be a clue to the multiverse? Some theories propose that the energy driving the expansion of our universe might be linked to interactions with other universes, with supernova serving as key indicators of these cosmic connections. Of course, these ideas remain highly theoretical, and there's much we don't yet understand. But that's the beauty of science. It's a journey into the unknown, driven by curiosity and the desire to uncover the secrets of existence. Supernova, with their immense power and complexity, are natural candidates for exploring these frontier questions. They remind us that the universe is full of surprises and that even the most familiar phenomena can hold unexpected depths. As we venture into this speculative realm, it's important to approach these ideas with both excitement and skepticism. The multiverse remains a hypothesis not yet proven, but it's a hypothesis that pushes the boundaries of what we know and challenges us to think bigger. Whether or not supernova truly hold the key to parallel universes, the pursuit of these questions enriches our understanding of the cosmos and our place within it. It's a reminder that the universe is not just a place of stars and galaxies, it's a mystery waiting to be unraveled, one explosion at a time. When we gaze at the night sky, we're not just looking out into space, we're also peering back in time. Every beam of light from a distant star or galaxy carries with it a story from the past, and supernova are no exception. These explosive events are more than just brilliant flashes in the cosmos. They are cosmic time machines offering us a glimpse into the universe's ancient history. Through their light, we can travel billions of years into the past, uncovering secrets about how the universe has evolved over eons. Consider this: light travels at a finite speed, roughly 300,000 kilometers per second. While that seems instantaneous to us, the vast distances of space mean that light from even relatively nearby stars can take years to reach Earth. For supernova, which often occur in galaxies millions or even billions of light years away, the light we see today actually left those stars long before humans walked the Earth. When we observe a supernova, we're witnessing an explosion that happened in the distant past, a snapshot frozen in time. This temporal aspect of supernova makes them invaluable tools for astronomers. By studying the light from these explosions, we can piece together the conditions of the universe at different points in its history. For example, the famous supernova 1987 occurred in the Large Magellanic Cloud, a neighboring galaxy. Its light took 168,000 years to reach us, meaning we're seeing the star as it was during the last ice age on Earth. It's like opening a time capsule, revealing a moment in cosmic history that would otherwise be lost. But the real magic happens when we look even farther back. Distant Type Ia supernova, which serve as standard candles for measuring cosmic distances, have allowed us to map the expansion of the universe over billions of years. By observing these explosions in galaxies billions of light years away, we can trace how the universe has grown and changed since its infancy. This has led to groundbreaking discoveries, like the realization that the universe's expansion is accelerating, a finding that introduced the concept of dark energy. What's truly remarkable is how supernova connect us to the broader story of the cosmos. Each explosion is a thread in the tapestry of the universe's history, weaving together moments of creation, destruction, and transformation. They remind us that the universe is not static. It's a dynamic, ever-changing entity, and we are privileged to witness its unfolding story through the light of these ancient explosions. As we continue to explore the cosmos, supernova will remain our guides through time, offering insights into the universe's past, present, and future. They are more than just fleeting flashes in the night sky. They are windows into the history of everything, inviting us to explore the mysteries of time itself. And with each new discovery, we come one step closer to understanding our place in this vast, interconnected cosmic narrative. As we peer into the vast expanse of the universe, it's impossible not to wonder, what lies ahead? Will the cosmos continue expanding forever, or is there a different fate in store? Supernova, those spectacular explosions marking the death of stars, might hold some of the answers. These cataclysmic events aren't just isolated acts of destruction. They're woven into the fabric of the universe's evolution, offering clues about its ultimate destiny. One of the most compelling questions in cosmology is how the universe will end. Scientists have proposed several scenarios, each with its own dramatic implications. The first, known as the Big Crunch, suggests that the universe's expansion could one day reverse. If gravity eventually overcomes dark energy, the mysterious force driving the universe's accelerated expansion, everything could collapse back into a single, infinitely dense point. Supernova play a role here too. As stars die and explode, they release energy and matter that influence the gravitational tug of war shaping the cosmos. The more supernova occur, the more they contribute to the mass and energy that could, in theory, pull the universe back together. On the other end of the spectrum lies the Big Freeze, a scenario where the universe continues expanding indefinitely, growing colder and darker over time. In this model, dark energy dominates, pushing galaxies farther and farther apart until stars burn out and matter becomes too dispersed to form new ones. Supernova, in this context, are like cosmic embers, brief flashes of light in an increasingly empty and cold universe. Each explosion marks the end of a star's life and the dispersal of its elements, but over time, these events become rarer as the universe's fuel for star formation dwindles. The Big Freeze paints a picture of a universe where supernova are the last fireworks in a fading cosmic show. Then there's the Big Rip, a more dramatic and violent end. In this scenario, dark energy doesn't just accelerate the universe's expansion, it becomes so powerful that it tears apart galaxies, stars, and even atoms themselves. If this were to happen, supernova would be among the final acts of cosmic destruction before everything is ripped apart. The shockwaves and energy released by these explosions would be swallowed by the relentless expansion, leaving behind a universe fractured beyond recognition. So, where do supernova fit into these grand cosmic narratives? They're more than just markers of stellar death, they're active participants in the universe's story. By studying the frequency, distribution, and impact of supernova, scientists can piece together how the universe has evolved and where it might be headed. For example, the rate of supernova in different galaxies can reveal how quickly stars are forming and dying, providing insights into the balance of dark energy and gravity. Each explosion is a data point, a clue in the puzzle of the universe's fate. But supernova don't just tell us about the end, they also remind us of the cycles that define the cosmos. Every explosion scatters heavy elements into space, seeding the next generation of stars and planets. In a way, supernova are both an end and a beginning, linking the death of stars to the birth of new possibilities. They are a testament to the universe's ability to transform, to create beauty even in the face of destruction. As we ponder the ultimate fate of the universe, supernovas serve as both a guide and a reminder. They show us the forces that shape the cosmos, from the pull of gravity to the push of dark energy. But they also remind us that the universe is a dynamic, ever-changing place, full of mystery and wonder. Whether the universe ends in a crunch, a freeze, or a rip, supernova will continue to light up the cosmos, offering glimpses of the past and hints of the future. And as we watch these cosmic explosions, we're not just witnessing the death of stars, we're catching a glimpse of the universe's grand, unfolding story. As humanity sets its sights on the stars, the cosmos presents both wonders and warnings. Among the most awe-inspiring yet perilous phenomena are supernova explosions so powerful they can outshine entire galaxies. While these cosmic events shape the universe in profound ways, they also pose significant challenges for human exploration. Imagine a future where astronauts journey to distant stars, only to find themselves in the path of a supernova's lethal radiation. This isn't just science fiction, it's a real concern as we push the boundaries of space travel. The dangers of a nearby supernova are not to be underestimated. If a star were to explode within a few dozen light-years of Earth, the intense radiation could strip away our planet's protective ozone layer, exposing life to harmful ultraviolet rays. For astronauts in space, the risks are even greater. Without the shielding of Earth's atmosphere, they would be vulnerable to the supernova's deadly gamma rays and cosmic rays, which could damage DNA and increase the risk of cancer. Even spacecraft shielding might not be enough to fully protect them, raising critical questions about the safety of long-term missions beyond our solar system. But the challenges don't end with radiation. Supernova also produce powerful shockwaves that can disrupt the interstellar medium, the thin gas and dust between stars. These shockwaves can compress gas clouds, triggering the formation of new stars and potentially altering the trajectories of cosmic particles. For spacecraft navigating through this dynamic environment, such disturbances could pose navigational hazards, making it harder to chart a safe course through the cosmos. It's a reminder that space is far from empty. It's a lively, ever-changing arena where even the most distant explosions can have far-reaching effects. Despite these risks, supernova also present incredible opportunities for scientific discovery. Studying these explosions up close, or at least closer than we've ever been, could unlock secrets about the life cycles of stars, the creation of heavy elements, and the fundamental forces that govern the universe. Future missions equipped with advanced detectors and telescopes could observe supernova in real time, capturing data that's impossible to gather from Earth. Imagine a spacecraft positioned to witness the birth of a neutron star or the formation of a black hole, offering a front-row seat to some of the universe's most dramatic events. For now, the prospect of encountering a supernova during a human mission remains a distant concern. Most supernova occur in galaxies far beyond our own, and the likelihood of one happening close to Earth is extremely low. But as we venture farther into the cosmos, the potential for such an encounter grows. This underscores the importance of understanding these explosive events and developing technologies to mitigate their risks. From advanced shielding materials to early warning systems, the challenges posed by supernova are driving innovation in space exploration. Supernova remind us that the universe is both beautiful and unpredictable. They are forces of creation and destruction, shaping the cosmos while posing challenges for those who seek to explore it. As we prepare to journey beyond our solar system, these cosmic explosions serve as a humbling reminder of the dynamic and sometimes dangerous nature of the universe. Yet they also inspire us to push forward, to uncover the secrets of the stars, and to prepare for the wonders and hazards that await us in the vast expanse of space. The future of human exploration is bright, but it's also a journey into the unknown where the lessons of supernova will light our way. The beauty of a supernova isn't confined to the realms of science. It transcends into the world of art, where its explosive brilliance has ignited the imaginations of creators for centuries. These cosmic explosions, with their swirling clouds of color and raw, untamed energy, have become symbols of both destruction and rebirth, inspiring artists to capture their magnificence in every medium imaginable. From the delicate brushstrokes of classical paintings to the bold lines of modern digital art, supernova have left an indelible mark on the creative world. One of the earliest depictions of a supernova can be traced back to the ancient world, where celestial events were often seen as divine messages. Rock carvings and cave paintings, though not always explicitly identified as supernova, hint at humanity's fascination with the skies. Fast forward to the Renaissance, and artists like Albrecht Dürer began to incorporate astronomical phenomena into their works, blending science and art in ways that reflected the era's growing curiosity about the cosmos. These early representations, while not always scientifically accurate, captured the awe and wonder that supernova evoke. In more recent times, supernova have become a staple of modern and contemporary art. Take, for example, the works of abstract expressionists like Jackson Pollock, whose chaotic, energetic canvases seem to mirror the explosive chaos of a dying star. Sculptors, too, have embraced the theme, creating intricate pieces that evoke the swirling debris and luminous aftermath of a supernova. Digital artists, armed with cutting-edge tools, have taken the concept even further, crafting hyper-realistic renderings that bring these cosmic explosions to life in stunning detail. These works don't just depict supernova, they invite us to feel their power, to experience the awe of witnessing a star's final, glorious act. What makes supernova such a compelling subject for artists is their duality. They are both destructive and creative, endings and beginnings, and this tension resonates deeply with the human experience. In art, they often symbolize transformation, resilience, and the beauty of impermanence. A painting of a supernova might capture the vibrant hues of its expanding shockwave, while a sculpture might focus on the intricate patterns of its remnants. Each piece tells a story not just about the explosion itself, but about the emotions it inspires: awe, wonder, and a deep connection to the vastness of the universe. Supernova also serve as a bridge between science and art, two disciplines often seen as separate but deeply intertwined. Artists draw inspiration from the latest astronomical discoveries, using their work to communicate complex ideas in ways that are accessible and emotionally resonant. In turn, scientists often find beauty in the artistic interpretations of their research, reminding them of the human element behind the data. This collaboration enriches both fields, creating a dialogue that deepens our understanding of the cosmos and our place within it. So, the next time you gaze at a painting or sculpture inspired by a supernova, take a moment to appreciate not just the artistry but the story it tells. These works are more than just representations of cosmic events. They are expressions of our collective fascination with the universe, a testament to the enduring power of creativity to illuminate the unknown. Through art, supernova become more than distant explosions. They become a shared experience, a reminder of the beauty and mystery that surrounds us all. The drama of supernova isn't confined to the realms of science and art. It echoes through the world of music as well. Composers, captivated by the raw power and cosmic beauty of these stellar explosions, have woven their themes into symphonies, operas, and modern compositions. Supernova, with their explosive energy and profound symbolism, have become more than just astronomical events. They are inspirations for sound, resonating not only in space but also in the melodies and harmonies that fill concert halls and headphones. Today, let's explore how the music of the stars has found its way into the music of humanity. One of the most striking examples of supernova in music comes from Gustav Holst's orchestral suite, The Planets. While not explicitly about supernova, the piece captures the grandeur and mystery of the cosmos, evoking the same sense of awe that these explosions inspire. The movement Mars, the bringer of war, is particularly fitting, with its relentless, driving rhythms and explosive crescendos that mirror the violence and energy of a supernova. Holst's work reminds us that the cosmos is not just a silent void. It's a symphony of forces, a dance of creation and destruction that composers have long sought to capture. In the realm of opera, supernova have also made their mark. John Adams' Dr. Atomic, which tells the story of the development of the atomic bomb, draws parallels between the explosive power of nuclear weapons and the cataclysmic energy of supernova. The opera's haunting score, with its tension-filled strings and apocalyptic crescendos, reflects the dual nature of these events, both as moments of immense destruction and as sources of new beginnings. It's a powerful reminder that the themes of supernova transformation, energy, and the fragility of existence resonate deeply with the human experience. Modern composers have taken the connection between supernova and music even further. Electronic artists like Jean Mitchell-Jarre and ambient musicians such as Brian Eno have used supernova as muses, crafting soundscapes that evoke the vastness and mystery of the cosmos. These compositions often blend synthetic tones with natural sounds, creating an otherworldly atmosphere that transports listeners to the heart of a dying star. The result is music that feels both ancient and futuristic, a sonic representation of the universe's endless cycles of birth and death. But it's not just classical or electronic music that draws inspiration from supernova. Rock and metal bands have also embraced the theme, using it to explore themes of power, transcendence, and cosmic wonder. Bands like Muse and Dream Theater have penned songs that reference supernova, their soaring guitar solos and thunderous drum beats mirroring the explosive energy of these celestial events. In these tracks, the supernova becomes a metaphor for moments of intense emotion or transformation, a symbol of the human capacity for both destruction and renewal. What makes supernova such a compelling theme in music is their universality. They are events of immense scale and significance, yet they also carry deeply personal meanings. For composers and listeners alike, they represent the beauty of impermanence, the power of transformation, and the mystery of the unknown. Whether through the sweeping orchestral movements of a symphony or the raw energy of a rock anthem, supernova remind us that the universe is not just something we observe, it's something we feel, something we hear, something that moves us in ways words alone cannot express. As we listen to the music inspired by supernova, we're reminded of the profound connection between the cosmos and human creativity. These compositions are more than just tributes to stellar explosions. They are expressions of our shared fascination with the universe, a way to translate the ineffable into something tangible. Through music, supernova become more than distant events. They become part of our story, a reminder that the beauty of the cosmos is not just out there, but also within us. So, the next time you hear a piece of music that moves you, take a moment to consider the stars. They might just be singing along. Supernova, those dazzling cosmic explosions, do more than illuminate the night sky. They illuminate the very questions that have puzzled humanity for centuries. These stellar events born from the death of massive stars are not just scientific phenomena. They are philosophical touchstones, inviting us to contemplate the nature of existence, the passage of time, and our place in the vastness of the universe. What does it mean to witness the death of a star, an event so powerful it reshapes the cosmos? And what can these explosions teach us about life, death, and the interconnectedness of all things? At their core, supernova challenge our understanding of time. When we observe a supernova, we're not just seeing a star explode, we're peering into the past. The light from these events often travels for millions or even billions of years before reaching us, offering a glimpse into a universe that no longer exists as it once did. This temporal disconnect forces us to confront the fluidity of time itself. Is the past truly gone, or does it linger in the light that reaches us? Supernova remind us that time is not a straight line but a tapestry woven from moments both near and far, connecting us to the ancient history of the cosmos. These explosions also provoke profound questions about the nature of reality. A supernova is a fleeting event, lasting only weeks or months, yet its impact reverberates across eons. It scatters the elements necessary for life, shapes the evolution of galaxies, and leaves behind remnants that continue to influence the universe long after the explosion fades. In this way, supernova blur the line between destruction and creation, challenging us to rethink our assumptions about beginnings and endings. Is destruction merely a prelude to something new? And if so, what does that mean for the cycles of life and death we experience on Earth? Supernova also invite us to reflect on our place in the universe. These explosions are both humbling and empowering, humbling in their scale and power, yet empowering in the knowledge that the very elements they create are the building blocks of life. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all forged in the hearts of stars that exploded long ago. In a very real sense, we are the children of supernova, born from the ashes of these cosmic giants. This realization connects us to the universe in a deeply personal way, reminding us that we are not separate from the cosmos but an integral part of its story. Philosophically, supernova also push us to consider the meaning of life in a universe governed by cycles of creation and destruction. If stars can die and give rise to new stars, planets, and even life, what does that say about our own existence? Are we too part of a larger cycle, destined to contribute to the ongoing evolution of the universe? These questions don't have easy answers, but they encourage us to think beyond our immediate concerns and consider our role in the grand tapestry of existence. Ultimately, supernovae are more than just explosions in the night sky. They are mirrors reflecting our deepest questions and aspirations. They challenge us to look beyond the surface of things, to seek meaning in the chaos, and to find beauty in the fleeting. Whether we're contemplating the nature of time, the interconnectedness of all things, or the mysteries of existence itself, supernova remind us that the universe is not just a place of stars and galaxies, it's a source of endless wonder and inspiration. As we continue to explore these cosmic explosions, we're not just learning about the universe, we're learning about ourselves. Imagine a classroom where students aren't just reading about the stars, they're exploring them. Where the mysteries of the cosmos come alive, not through dry textbooks, but through the awe-inspiring spectacle of a supernova. These cosmic explosions, with their raw power and profound beauty, are more than just scientific phenomena, they're powerful tools for education. By bringing the wonder of supernova into classrooms, museums, and outreach programs, we can ignite a passion for science in the next generation, inspiring young minds to ask big questions and dream even bigger. One of the most effective ways to use supernova in education is through hands-on learning experiences. Programs like NASA, a universe of learning, and the European Space Agency's educational initiatives offer students the chance to analyze real data from telescopes, track the light curves of supernova, and even simulate the explosion process using computer models. These activities don't just teach science, they let students do science, giving them a taste of what it's like to be an astronomer. When a student sees the data from a supernova and realizes they're looking at the death of a star billions of light years away, it's a moment that can spark a lifelong love of discovery. Outreach initiatives also play a crucial role in bringing supernova to the public. Planetariums and science centers around the world often feature immersive shows that recreate the explosive brilliance of a supernova, complete with stunning visuals and soundscapes. These experiences aren't just entertaining, they're educational, helping audiences of all ages grasp the scale and significance of these cosmic events. For many, it's the first time they truly understand that the elements in their bodies, the calcium in their bones, the iron in their blood, were forged in the hearts of stars that exploded long ago. This connection between the cosmos and everyday life is a powerful way to make science relatable and exciting. Digital resources have also revolutionized how we teach about supernova. Websites like Zooniverse allow anyone, anywhere, to participate in real scientific research by classifying supernova images or analyzing data. This citizen science approach not only contributes to actual research, but also empowers people to feel like they're part of something bigger. For students, it's a chance to see science as a collaborative, ever-evolving field, not just a static set of facts to memorize. Apps and online platforms such as Stellarium and Sky Safari bring the night sky to life, letting users explore supernova remnants and learn about their history from the comfort of their phones or computers. But perhaps the most transformative aspect of using supernova in education is their ability to inspire curiosity. These explosions are inherently dramatic, capturing the imagination in ways that few other phenomena can. When students learn about the life cycle of stars, the creation of elements, or the forces that shape the universe, they're not just memorizing facts, they're engaging with the story of the cosmos. Supernova become a gateway to broader topics, from physics and chemistry to philosophy and even art. They show that science isn't just about equations and experiments, it's about wonder, exploration, and the thrill of discovery. Educators and scientists are also finding creative ways to weave supernova into interdisciplinary learning. For example, art students might create paintings or sculptures inspired by supernova imagery, while history classes could explore how ancient cultures interpreted these celestial events. By connecting supernova to different subjects, we help students see the interconnectedness of knowledge and the relevance of science to their everyday lives. It's a reminder that the universe isn't just something we study, it's something we're a part of. Supernova are more than just cosmic explosions. They're catalysts for curiosity, creativity, and connection. By bringing these celestial wonders into classrooms and communities, we're not just teaching science, we're fostering a sense of wonder and possibility. And who knows, the next great astronomer, physicist, or science communicator might just be sitting in a classroom right now, inspired by the brilliance of a dying star. Through education and outreach, we can ensure that the legacy of supernova isn't just written in the stars, it's written in the minds and hearts of the next generation. The study of supernova isn't just about understanding the universe, it's also about pushing the limits of human ingenuity. These explosive events, so distant and fleeting, have sparked a wave of technological advancements that extend far beyond astronomy. From the telescopes we use to observe them to the supercomputers that simulate their complex physics, supernova have become a driving force for innovation. In this section, we'll explore how these cosmic explosions have shaped the tools of modern science and what that means for the future of discovery. At the heart of this technological revolution are telescopes, our windows to the cosmos. Observing a supernova requires instruments of extraordinary precision, capable of capturing light from billions of light years away. Over the years, the demand to study these explosions has driven the development of ever more advanced telescopes. Take, for example, the Hubble Space Telescope, which has provided stunning images of supernova remnants like the Crab Nebula. But the quest to understand supernova didn't stop there. Newer observatories, such as the James Webb Space Telescope, are equipped with infrared capabilities that allow us to peer through cosmic dust and observe the aftermath of supernova in unprecedented detail. These instruments aren't just tools for astronomers, they're marvels of engineering, born from the need to unravel the mysteries of the universe. But telescopes are only part of the story. The sheer complexity of supernova, from the physics of their explosions to the behavior of their remnants, requires computational power that goes far beyond traditional methods. Enter supercomputers, the unsung heroes of modern astrophysics. These machines, capable of performing trillions of calculations per second, allow scientists to simulate the intricate processes that occur during a supernova. By modeling everything from shockwaves to neutrino emissions, researchers can test theories, make predictions, and gain insights that would be impossible through observation alone. Supernova have essentially created a demand for computational innovation, pushing the boundaries of what's possible in both hardware and software. The technological impact of supernova extends even further, influencing fields beyond astronomy. For instance, the algorithms developed to analyze supernova data are now being used in medical imaging, helping doctors detect diseases with greater accuracy. Similarly, the materials science behind telescope mirrors has found applications in everything from satellite communications to renewable energy. It's a reminder that the pursuit of knowledge often leads to unexpected breakthroughs with benefits that ripple across society. Looking ahead, the study of supernova promises to continue driving technological progress. Upcoming missions like the Vera-C, Rubin Observatory, and the European Space Agency's Euclid telescope will generate vast amounts of data, requiring even more sophisticated tools for analysis. Artificial intelligence and machine learning are poised to play a pivotal role, helping researchers sift through this information to uncover new insights. And as we venture deeper into space, the technologies developed to study supernova will likely become essential for exploring other cosmic phenomena, from black holes to distant galaxies. What's truly remarkable is how supernovae serve as both subjects of study and catalysts for progress. They challenge us to build better tools, think more creatively, and push the limits of what we can achieve. In this way, the story of supernova isn't just about stars. It's about the human spirit of exploration and innovation. As we continue to unlock the secrets of these cosmic explosions, we're not just expanding our understanding of the universe, we're shaping the future of science and technology itself. The study of supernova isn't just a scientific pursuit, it's a global endeavor that brings together minds from every corner of the world. These cosmic explosions, with their immense scale and complexity, require a level of collaboration that transcends borders, languages, and disciplines. From the telescopes that capture their light to the supercomputers that simulate their physics, every discovery is the result of countless individuals working together toward a common goal. Supernova remind us that science is not a solitary journey but a shared adventure, one that thrives on the power of teamwork. One of the most striking examples of this global effort is the rapid response to supernova observations. When a supernova is detected, astronomers around the world spring into action, coordinating observations across multiple telescopes and instruments. This international network, often referred to as a follow-up campaign, ensures that no detail is missed. Telescopes in Chile might capture the early stages of the explosion, while observatories in Hawaii or Australia track its evolution over time. By pooling their resources and expertise, scientists can piece together a comprehensive picture of these fleeting events, turning a single observation into a global data set that enriches our understanding of the cosmos. But collaboration doesn't stop at observation. The analysis of supernova data is a massive undertaking, often requiring the combined efforts of astrophysicists, computer scientists, and engineers. For example, projects like the Supernova Cosmology Project and the Dark Energy Survey involve hundreds of researchers from dozens of institutions, each contributing their unique skills and perspectives. This collective approach allows for a deeper exploration of supernova, from the physics of their explosions to their role in shaping the universe. It's a testament to what can be achieved when people come together, united by a shared curiosity and a commitment to discovery. Of course, collaboration on this scale isn't without its challenges. Working across borders often means navigating differences in funding, infrastructure, and even time zones. Language barriers and cultural differences can add another layer of complexity. Yet, these challenges are also opportunities, chances to learn from one another, to build bridges, and to create a more inclusive scientific community. The study of supernova has shown that when we embrace diversity and work together, the results can be extraordinary. What's truly inspiring about this global effort is how it reflects the universal nature of science itself. Supernova don't belong to any one country or culture. They are cosmic events that transcend human boundaries. By studying them, we're reminded of our shared humanity and our collective place in the universe. Each discovery, each breakthrough, is a testament to what we can achieve when we set aside our differences and focus on what unites us, a desire to understand the cosmos and our place within it. The story of supernova is more than just a tale of stars and explosions. It's a celebration of human ingenuity and cooperation. It shows us that the pursuit of knowledge is not just about answering questions, but about coming together as a global community. As we continue to explore these cosmic wonders, we're not just uncovering the secrets of the universe, we're building connections that span the globe, reminding us that science is, and always has been, a shared endeavor. And in that spirit of collaboration, we find not only answers but also hope. A hope that together we can achieve the extraordinary. As we delve deeper into the mysteries of supernova, it's not just the science that demands our attention, it's also the ethical questions that arise from our pursuit of knowledge. These cosmic explosions, while awe-inspiring, force us to confront the broader implications of our research. How do we balance the quest for understanding with the resources we consume, the communities we impact, and the responsibilities we hold as scientists and explorers? Supernova, in their brilliance, shine a light not only on the universe but also on the ethical dimensions of our cosmic curiosity. One of the most pressing ethical considerations is the allocation of resources. Studying supernova requires cutting-edge technology, from massive telescopes to powerful supercomputers, all of which come with significant financial and environmental costs. For example, building and maintaining observatories in remote locations often involves large-scale construction and energy consumption. While the scientific rewards are undeniable, we must ask, are these investments justified in a world where resources are finite and urgent needs exist closer to home? This isn't just a question for policymakers, it's a conversation that scientists, ethicists, and the public must engage in together. Striking the right balance between advancing knowledge and addressing immediate human needs is a challenge that grows more complex as our ambitions expand. Another critical issue is the impact of scientific research on local communities, particularly when observatories are built in remote or culturally significant areas. Take, for example, the construction of telescopes on sacred indigenous lands, such as Mauna Kea in Hawaii. While these sites offer unparalleled views of the cosmos, their development has sparked debates about cultural preservation, environmental stewardship, and the rights of indigenous peoples. These conflicts remind us that the pursuit of scientific discovery doesn't happen in a vacuum. It intersects with the lives, traditions, and values of the people who inhabit these spaces. As we reach for the stars, we must also listen to the voices on the ground, ensuring that our quest for knowledge respects and uplifts the communities it touches. Beyond these tangible concerns, supernova also challenge us to think about the ethical responsibilities of scientists themselves. The knowledge we gain from studying these explosions has the potential to reshape our understanding of the universe, but it also carries profound implications. For instance, discoveries related to supernova have already transformed fields like cosmology and particle physics, influencing everything from our understanding of dark energy to the origins of the elements. With such power comes a responsibility to use this knowledge wisely, to communicate it clearly, to avoid sensationalism, and to ensure that it benefits humanity as a whole. Scientists are not just observers of the cosmos, they are stewards of its truths, tasked with sharing their findings in ways that inspire rather than alienate, and that foster understanding rather than division. At the heart of these ethical considerations is a fundamental question. Why do we explore? Is it simply to satisfy our curiosity, or is there a deeper purpose? Supernova, in their explosive beauty, remind us that exploration is not just about answering questions, it's about asking better ones. It's about understanding our place in the universe and using that knowledge to build a better future. This requires humility, empathy, and a willingness to engage with the complexities of our world. It means recognizing that every discovery, no matter how distant or abstract, has the potential to impact lives here on Earth. As we continue to study supernova, we must carry these ethical questions with us, allowing them to guide our work and shape our decisions. The universe is vast and full of wonder, but it is also a mirror, reflecting back the values and priorities of those who seek to understand it. By embracing the ethical dimensions of cosmic exploration, we can ensure that our journey into the stars is not just a scientific endeavor, but a deeply human one that honors the past, enriches the present, and paves the way for a brighter future. Even with all the incredible discoveries we've made about supernova, there's still so much we don't understand. These cosmic explosions, while awe-inspiring, are also deeply enigmatic. They challenge our knowledge, push the boundaries of physics, and remind us that the universe is far more complex and mysterious than we often imagine. From the intricate details of how they explode to the strange objects they leave behind, supernova are a constant source of unanswered questions, and that's what makes them so fascinating. Take, for example, the exact mechanisms behind a supernova explosion. While we know the basics, how a star's core collapses, how shockwaves tear through its outer layers, the fine details remain elusive. Why do some stars explode asymmetrically with jets of material shooting out in specific directions? What role do magnetic fields play in shaping the explosion? And how do neutrinos, those ghostly particles that stream out of the collapsing core, influence the process? These are questions that continue to puzzle scientists, even as they develop increasingly sophisticated models and simulations. The more we learn, the more we realize how much we still have to uncover. Then there's the mystery of what happens after the explosion. We know that supernova leave behind remnants, neutron stars, black holes, or glowing clouds of gas and dust, but the exact conditions that determine which remnant forms are still unclear. Why do some collapsing stars become neutron stars, while others collapse further into black holes? And what happens in the moments immediately after the explosion, as the star's core undergoes its final transformation? These are questions that probe the very limits of our understanding of matter, gravity, and the laws of physics. Even the remnants themselves hold secrets. Neutron stars, for instance, are some of the densest objects in the universe, with gravity so strong that it bends light and warps space-time. Yet, we're still trying to figure out what exactly happens inside them. Are their cores made of exotic forms of matter, like strange quarks or hyperions? And what about black holes, those regions of space-time where gravity is so intense that nothing, not even light, can escape? While we've made incredible strides in studying them, from detecting gravitational waves to capturing the first image of a black hole's event horizon, there's still so much we don't know about their inner workings or their role in the cosmos. But perhaps the most profound mystery is how supernova fit into the larger story of the universe. They're not just isolated events, they're part of a cosmic cycle, shaping galaxies, seeding new stars, and even influencing the potential for life. Yet, we're still piecing together how these explosions have shaped the evolution of the universe over billions of years. How have they contributed to the distribution of elements? How do they affect the formation of new stars and planets? And what role do they play in the ultimate fate of the cosmos? These are questions that connect the smallest particles to the largest structures in the universe, weaving a tapestry of complexity that we're only beginning to unravel. What's remarkable is that these unanswered questions aren't just scientific puzzles, they're invitations to explore. They remind us that the universe is a place of endless wonder, full of surprises that challenge our assumptions and expand our horizons. Supernova, in all their explosive brilliance, are a testament to the beauty of the unknown. They show us that science isn't about having all the answers, it's about asking the right questions and embracing the journey of discovery. And as we continue to probe the mysteries of these cosmic explosions, we're not just uncovering the secrets of the stars, we're deepening our connection to the universe and to each other. So let's celebrate the unknown, for it's in the unknown that the most extraordinary discoveries await. As our journey into the heart of a supernova comes to a close, we're left with more than just knowledge. We're left with a profound sense of connection to the cosmos. These dazzling explosions are far more than fleeting moments of destruction. They are cosmic storytellers, revealing the intricate processes that shape the universe as we know it. From the very elements that make up our world to the formation of some of the most mysterious objects in existence, supernova remind us that the universe is a place of endless transformation and wonder. What's truly remarkable is how these explosive events tie us to the broader narrative of existence. The iron in our blood, the gold in our jewelry, and the oxygen we breathe, all of it was forged in the fiery hearts of stars that met their end in spectacular fashion. Supernova are not just distant phenomena, they are part of our story, the cosmic legacy written into the fabric of our being. They teach us that even in destruction there is creation, and that every ending gives rise to new beginnings. But the story of supernova doesn't end with their explosions. These events ripple through the universe, influencing everything from the formation of new stars to the evolution of entire galaxies. They are cosmic architects shaping the universe in ways we're only beginning to understand. And as we continue to study them, we uncover not just the secrets of the cosmos, but also the profound interconnectedness of all things. Every supernova is a reminder that we are part of something much larger than ourselves, a vast, dynamic universe that is constantly evolving. We hope this exploration has ignited a spark of curiosity and wonder within you. The next time you look up at the night sky, remember that those twinkling stars are not just distant lights, they are the birthplaces of elements, the remnants of explosions, and the seeds of future worlds. Supernova invite us to dream, to question, and to marvel at the beauty and complexity of the universe. Thank you for joining us on this cosmic adventure. If you've enjoyed this journey, don't forget to like, share, and subscribe for more deep dives into the mysteries of the universe. Whether it's black holes, distant galaxies, or the origins of life itself, there's always more to discover. Until next time, keep exploring, keep wondering, and keep looking up at the stars. The cosmos is waiting for you.